Good morning. This is the last class of our module 1. So with this we have reached at the end of module 1. So along with this video I will be uploading a few questions and problems, and definitely you can expect problems from this module. So I will upload some solved problems which you must work out. You can expect a question problems. Definitely they will ask problems from this session, okay, for your exam. So just go through the solved problems that I upload along with this video. So in today's session we are going to learn about absolute scale of temperature, which we all know. You all know that in order to measure temperature we use thermometers, and we can use different substances in thermometers. Usually the substance that we use is mercury. So depending upon the nature of that substance, we get different scale of temperature. So the temperature measured with the different thermometers will not agree with one another. So we need an ideal thermometric scale to measure temperature. So such a scale was developed by Lord Kelvin in the year 1848, and that new scale of temperature that was developed is called absolute scale of temperature or Kelvin scale of temperature. Now, to develop an absolute scale of temperature, the measuring temperature, the necessary condition is that the measuring temperature must be independent of the thermometric substance. That is, we have one such system, that is the Carnot engine. We know that efficiency of Carnot engine depends only on the temperature of source and sink. That is, it depends only on the work done by the engine, just depends on the temperature difference between the source and sink. So this idea can be utilized to measure T1 minus T2. Now this difference in temperature, or T1 minus T2, is independent of the working substance. So this idea is utilized in order to develop an ideal thermometric scale. Now let us see the theory, which is very simple. So consider a Carnot engine working between theta 1 and theta 2 temperature measured on an arbitrary scale. Let Q1 be the amount of heat absorbed at theta 1, and let Q2 be the amount of heat rejected at theta 2. So what is efficiency eta? Q1 minus Q2 by Q1, that is again equal to 1 minus Q2 by Q1, that is again is equal to 1 minus theta 2 by theta 1, and that can be expressed as a function of theta 1 and theta 2. So briefly we can write Q2 by Q1 is equal to 1 minus f theta 1 theta 2. So again rewriting, we are just taking the reciprocal on LHS and RHS. So Q2 by Q1 will now become Q1 by Q2, that is again equal to 1 by 1 minus f of theta 1 comma theta 2. Now that quantity, let us represent it as a function of, that is capital F of theta 1 theta 2. Now that f is actually another function of theta 1 and theta 2. Now suppose that you are having a Carnot engine working between theta 2 and theta 3 with theta 2 greater than theta 3, which absorbs Q2 heat and rejected Q3 heat. So in such case what will be Q2 by Q3? It will be a function of theta 2 theta 3. Now again if it works between theta 1 and theta 3 with theta 1 greater than theta 3, then what will be Q1 by Q3? It will be f of theta 1 theta 3. So now just multiply equation 1 and 2, then you get Q1 by Q2 into Q2 by Q3. Q2 and Q2 will get cancelled, right? So you will get it as Q1 by Q3, that is equal to function of theta 1 theta 2 into function of theta 2 theta 3. So again this Q1 by Q3 can be written as f of theta 1 theta 3. So f of theta 1 theta 3 is equal to f of theta 1 theta 2 into f of theta 2 theta 3. This is called function equation. So here in the above equation LHS contains no theta 2. So RHS also should be independent of theta 2. Now this is possible only if we choose f of theta 1 theta 2 as phi of theta 1 by phi of theta 2, and f of theta 1 theta 3 as phi of theta 2 by phi of theta 3. What is phi? It is another function of temperature. Therefore f of theta 1 theta 3 can be obtained by multiplying these two quantities, that is phi of theta 1 by phi of theta 2 into phi of theta 2 by phi of theta 3. So theta 2 and theta 2 get cancelled. So what is remaining is phi of theta 1 by phi of theta 3. Since theta 1 is greater than theta 2 and theta 2 is greater than theta 3, the function phi of theta 1 also should be greater than the function phi of theta 2. Now this phi of theta is a linear function of theta and it can be used to measure temperature. Later, Lord Kelvin suggested that this phi of theta should be proportional to theta, that is phi of theta 1 should be proportional to theta 1 and phi of theta 2 should be proportional to theta 2. So the final equation what we have is q1 by q2 is equal to theta 1 by theta 2 or q1 by q3 is equal to theta 1 by theta 3. This equation shows that the ratio of two temperatures on this scale is equal to the ratio of heat absorbed to heat rejected. This temperature scale is called Kelvin thermodynamic scale of temperature. Next is an equation. This is the last session, Clausius-Clapeyron equation. Suppose that you are having a phase change either from solid to liquid or liquid to vapor and vice versa, and suppose that that phase change is occurring at constant temperature and pressure. Now this constant temperature we call it by the name melting point if it is in the case of solid to liquid phase change, and we call that constant temperature as boiling point if it is the case of liquid changing to vapor phase. Okay, so now what we are our intention is to understand what will happen to this constant temperature when pressure changes. So such equation is given by Clausius-Clapeyron equation. So it is nothing but a relation between change in temperature with respect to pressure change during a phase change. Okay, that is the definition. And now consider this figure. Here you can see two isothermals, that is EBAF and GHIJ. Okay, for a substance at temperature T and T minus DT respectively. Now if the change of state involved is from vapor to liquid, that is from E to F and G to J, then we have the substance exist only in vapor phase at B and H. Then at A and I, the substance is at its liquid phase only. Now let's see the isotherms BA and HI. The substance exists in both phases, that is both in liquid phase and vapor phase. So this is because change of state of the substance is in progress. That is why we are having the coexistence of two phases, that is both liquid phase and vapor phase. Now when the substance is at A, we already said that it is in the liquid state. Inside that case, the temperature T actually represents the boiling point at pressure P. Now at the point I, the substance is in the vapor phase and the temperature T minus DT actually represents the boiling point at pressure P minus dP. Okay, now consider the adiabatics, that is AD and BC. Consider the adiabatics AD and BC and let it join the isotherms AB and DC. If that joins, we will get a complete reversible cycle ABCD. Okay, so the work done in that complete cycle ABCD is given by dW by Q1 is equal to dt by T. So using work done in a cyclic process is equal to area of closed loop, we can write that dW as area of that parallelogram, which is nothing but length into breadth. Length is the change in volume V2 minus V1 and breadth is dP. So if the mass of substance is unity, heat absorbed during the change of state is the called latent heat, that is Q1 is given the name L, latent heat. Now you are using the values of dW and Q1 in equation 1. Okay, so we get it as dP v2 minus v1 by L is equal to dt by dt, or dp by dt is equal to L by T v2 minus v1. This is Clausius-Clapeyron equation or first latent heat equation. What is dp? Change in pressure. What is dt? Change in boiling point or melting point. So this equation, that is Clausius-Clapeyron equation, shows that for a given change in pressure, dt will be either positive or negative depending on the sign of volume change v2 minus v1. Now for solids which expands on melting, for that v2 minus v1 will be positive, that is dp by dt will also be positive. This means that pressure increases, melting point also increases, and vice versa. Okay, when the solid, and in the case of solids which contract on melting, what will be v2 minus v1? It will be negative, so dp by dt will also be negative. Now let us consider the case of boiling. Suppose that a liquid changes from its liquid state to vapor state. In such case v2 minus v1 is positive, so dp by dt will also be positive. Therefore boiling point of the liquid increases with increase in pressure. That is why water boils at low temperature at high altitudes. Now there are two special cases. One is when v1 equal to v2, or when the volume difference v2 minus v1 is 0. That is, the change in specific volume is 0. This happens either L equal to 0 or dp by dt equal to infinity. When L is equal to 0, it means that liquid goes to vapor state and no heat is absorbed. This happens at a temperature close to critical point. Now in case 2, that is dp by dt is equal to infinity or very large at fusion for most of the solids. So with this we have come to the end of our module 1. So along with that, I will upload a few problems, old problems. So please go through all those problems, because you can definitely expect a problem from this session. Okay, thank you.